Previously on the head of a pen.
The way we do experiments today really comes out of what they were doing 100 years ago. Taking particles, shooting them at material, and seeing what comes out.
We have enough energy to create these supersymmetric particles, should they exist.
The process of production of black holes has been happening all around us, all around the universe, all around the Earth, quite frequently through cosmic rays. So the energies that the Large Hadron Collider will explore are already being explored in the universe all the time by very energetic cosmic rays colliding with other particles in the universe.
At the time, the United States was bent on reestablishing itself as the leader of particle physics, and they didn't want to share in the glory with the Europeans. They wanted to build their own machine, the Superconducting Super Collider, which started out about $5 billion and ended up with a price tag of $10 billion, at which time the United States Congress killed it in 1993. So the idea of making a proton-proton collider didn't die with the SSC. Really the only place you could do it thereafter was to do like the Europeans had said at the beginning, take the superconducting magnet technology and put it in an existing tunnel.
E equals mc squared, our favorite equation, energy equals mass. The more energy you have, the more mass you can create, really just by colliding particles together. The energy that they have is available to make new massive particles, including, and very rarely, the Higgs boson. Now the advantage of the Large Hadron Collider, which is coming online in Europe now, is that it has 7 times more energy. That doesn't sound like much, but when you work out what is the production rate for Higgs bosons at the Large Hadron Collider, it's about 100 times larger than it is at the Tevatron. And the backgrounds, there's still background present at the Large Hadron Collider. They're not as big relative to the Higgs boson production as they are at the Tevatron.
Finally, we will discover this Higgs boson I talked about earlier, this particle that is responsible for things having mass, right? Or we will discover something else like it that does not correspond exactly to the theories that have been written down. But we will discover the reason why things have mass. That will probably be, I would guess that'd be the most important discovery. Why do objects like this desk and my shoe and your camera have a property called mass? All right, so that will come out of the Large Hadron Collider almost certainly.
There's nothing that tells us what the mass of the Higgs boson should be in the theory. We now have a fairly good idea, though, that it has a mass of about 120 times the mass of a proton or a neutron. Neutron and proton are very close together in mass. The way we know this is by measuring the masses of 2 other particles called the top quark and the W boson. The W boson is the carrier of the weak nuclear force. That's why it's called W. And its mass and the mass of the top quark, which is the heaviest one, it's it's about 170 times more heavy than a proton. Those 2 masses pin down what the mass of the Higgs boson should be to about, as I say, 120 times the mass of a proton.
It turns out that the field that is responsible for this mass is a massive field itself, because the Higgs field creates mass, it also gives mass to itself, and we know from previous experiments that the mass of the associated with this Higgs field is relatively large, so large that it has not been produced in any laboratory experiment so far, and in order to create a particle with big mass by Einstein's famous relation, mass is energy over the speed of light squared. So if you want to create a lot of mass or a heavy particle or a heavy field, you have to input a lot of energy into it. And the LHC will be the first experiment that's energetic enough to produce the Higgs particle or the Higgs field.
The luminosity, really, it's like the luminosity of a light, of a light source. When you have a really bright light source, it means many photons are coming at you from that light source. All right, and when you have a high luminosity particle accelerator, that means you've got many more chances for the particles to collide, because you've got many more particles in each beam. And they typically need that because at these high energies, the chances of any two particles colliding is really pretty low. So you've got to compensate for that by having high luminosity.
I should emphasize that the LHC is a fantastic machine, but the energies that are being attained there are not attained there for the very first time in the recent history of the universe. Such energies, higher energies, are attained when cosmic ray particles collide with particles in the atmosphere. The reason what makes LHC special is not just the high energy, it is the high luminosity, or the large numbers of particles that are colliding with each other at this high energy. And so the LHC is not just a high energy machine, it's a high luminosity machine.
In our detector, which is what in the laboratory reference frame, as we say, we have this proton coming in at the speed of light and this proton coming in at the speed of light. So yeah, an ordinary person would say, well, it must be that the other one proton sees the other one at twice the speed of light. But that's not the way relativity allows you to add velocities together.
From any frame of reference, not just the one that we sit around on Earth, the speed of light can never be greater, the speed of any object can never be greater than the speed of light. But you can see a lot more energy. And that's the key to the Large Hadron Collider, is that they are bringing tremendous amounts of energy together in one spot, right in the middle of a detector. Right. If, on the other hand, I took a beam of protons and smashed it into a single stationary target, let's say a gold foil, all right, most of that energy is just wasted throwing the protons and neutrons forward. Right? It doesn't go to making really massive energetic particles. If you bring them both together in a collision point, and they have a head-on collision, not a glancing blow, but a head-on collision, then you get the effect of the energy that's in both of those beams, both of those particles, to make something very massive, trillions of electron volts, in what we call the center of mass frame.
So two protons at the LHC are moving near the speed of light, and they are moving towards each other and bang with each other. Now, if you are riding on one of the protons and you are looking at the other one, then you will still see a situation where a proton is coming at you very near the speed of light. You will never manage to exceed the speed of light. Anytime any observer that measures the speed of any object relative to himself or herself will see that object moving at most at the speed of light relative to him. And that is a consequence of the special theory of relativity. This is the beginnings of the special theory of relativity. It is somewhat counterintuitive that you have two objects coming near the speed of light at each other, and when you ride on one of them, you see the other one still moving at the speed of light instead of twice, say, the speed of light. And that is intrinsic in the counterintuitive nature of special relativity.
It's all a matter of what reference frame you're measuring things in.
You can understand it provided you are very careful about how you measure distances and times, because velocity, or the speed of something, is how much distance it covers within a given amount of time. So you have to be careful how you measure distances and how you measure times. And you have to use only one basic principle to derive this counterintuitive result, that the speed of light is the same for every observer. You can't run, if you have a beam of light coming this way, from, let's say, from right to left, and if you move against that speed of light, you can't make light appear to move faster than the speed of light. And it's a consequence of that fact that any velocity that you'll measure relative to yourself will be at most the speed of light.
If you're riding on one of the protons inside the LHC tunnel, and you're riding on a proton which is about to get undergo one of these very high energy collisions, let's just slow it down in time a little bit. You're riding and you see coming at you a proton with extremely high energy at this more or less the speed of light, just shy of the speed of light. I could calculate how many nines it is, 99.999% of the speed of light. But what it would look like is a little disk, a little flattened disk. Why do I say that? Because in relativity, when something is moving very fast, its length contracts. So, in fact, the bunch of protons looks flattened too, from the perspective of a proton riding inside the LHC tunnel.
Yeah, in fact, if you trace carefully the amount of energy that is involved, including Einstein's equal mc squared, the energy that's stored in the mass, energy is always balanced according to any observer. If you analyze a given situation according to any observer's point of view, you will discover that the total amount of energy is always conserved.
In the reference frame of a proton in the LHC, the other proton has much higher energy than the proton would have in the reference frame of the laboratory.
When two particles, let's say you've got two protons in the Large Hadron Collider going at close to the speed of light, probably 0.9995 times the speed of light. All right, that's as viewed in the laboratory at CERN. And one is going 0.995 that way, and another is going 0.995 that way. All right, and but if you are riding on one of those protons, that doesn't mean that you're going to see the other proton coming at you with close to twice the speed of light. It doesn't work that way. I know it's counterintuitive. But all it means is that the energy, the effective mass or the energy of that incoming proton is a lot larger.
From the reference frame of one of the protons in the LHC, the other proton that's about to annihilate it has speed of light, but it doesn't have the same energy as it does in our reference frame in the laboratory either.